Hey there, welcome to a video discussing section 6.4, part 2 on the fundamental theorem of calculus, also called part 2. So starting at page 6, I know we didn't get to the end of page 5 for A period, but that's okay, we'll come back to that later. So let's focus on part 2 of the fundamental theorem of calculus. So remember at the end of section 5.3 that we had said that if f is continuous on the closed number from a to b, then we let capital F be any antiderivative of little f on that closed number from a to b. Then we can conclude that the definite integral from a to b of little f of x dx equals little a and little b, or the limits of by integration, plugged into the antiderivative, which we call capital F. And remember, because we have the plus c terms, any, basically refers to the plus c terms being canceled on the subtraction. That's why capital F could be any antiderivative. It doesn't really matter. Because remember, we do cancel out that plus c term when we do the antiderivative with the definite integral over here. So we've already done practice doing this. The only thing here is add a little extra notation. And I may have already done this with you guys, where when you do the definite integral, remember you're going to find the antiderivative of little f, and you're going to plug in a and b. And we do this bracket. I like to do like these vertical lines to show that I'm plugging a and b into the antiderivative. Yeah, that notation, that's kind of what I tend to prefer, but that's fine if you want to do that. I don't really care. So if we look at example 7, so again, F to C part 2, we have seen already. That was at the end of 5.3 notes. So nothing really, 6.3 notes. This is from the old textbook or the old edition. So let's look at example 7 here. We're integrating secant squared theta d theta from pi over 4 to pi over 3. We know the antiderivative of secant squared theta is tangent theta, because derivative of tangent theta is secant squared theta. You plug in pi over 3, plug in pi over 4, and you get, obviously use your unit circle. Tangent pi over 3 is like tangent 60 degrees as root 3. Tangent pi over 4 is like tangent 45 degrees 1. And there you go. So this right here is essentially fundamental theorem of calculus part 2, where you simply do the antiderivative and plug in your limits of integration. So that's what's happening there. Let's revisit area and have a discussion about net area and total area. So net area is basically evaluating the integral. Basically, the area under the curve is treated as negative and above is treated as positive. Total area is kind of like an absolute value in a way, where whether you're above or below the x-axis, you always treat the area as being positive. That's considered total area. So say, for example, you have the integral from a to b, and that area is 7. The integral from b to c, that area is -2. So the net area is simply going to be 7 plus -2, or 5. Whereas total area, you treat, it's like you're doing the absolute value of this. 7 plus 2 is 9. So let's look at example 8 here. Say you want to find the total area of this curve, y equals x squared minus 4, and the x-axis from an integral from -1 to 4, or the interval from -1 to 4. So we could do, we'll set this up correctly. You can see where we cross the x-axis, which is going to be at 2. So you could just integrate from, excuse me, -1 to 2 of our function. And then also integrate from 2 to 4 of our function. And once you find what this is, because that's a negative area, you're going to do the absolute value of that. Because that's going to be a negative area, because it's below the x-axis. And of course, that's going to be a positive area, because it's above the x-axis. Now, the one thing that I could teach you guys on how to do antiderivatives more efficiently, when you have x squared or anything that's x to the n power, and you're taking the antiderivative of it, you could just add 1 to the exponent and divide by a new exponent. And of course, plus c, right? That's something that you could do if you have a power function, because it's kind of the opposite of doing the derivative, right? Like if I were to do the derivative, of course, d dx of this, we know this now is n times x to the n minus 1 power. And remember, FTC states that if I do the integral of the derivative or derivative of the integral, you get back to the original thing. Well, if I were to add 1 to my exponent, that would now become x to the n power and divide by a new exponent. And you see that those cancel. You just get x to the n. So that's something you could do to, instead of trying to think intuitively, which is good. I mean, I wanted you guys to think intuitively, like deriv what expression gets you x squared, which would be 1/3 x cubed. But what you could now do is just say, hey, let me add 1 to that exponent and divide by a new exponent. And 4, there's no x here. So you assume it's x to the 0 power. So add 1 to it becomes x to the 1 and divide by the new exponent, which is 1. So you just get 4x. And don't worry about the plus c because it will cancel for a definite integral. So now you plug in 2. So you get 8/3 minus 8. Plug in -1, you get -1/3 minus -4, which becomes plus 4. So you have 8/3 minus -1/3 is 9/3. -8 minus 4 is -12. And you should get -9, because that's 3 minus 12, so you get -9. Now for over here, I'll do this in green for a bit of contrast. Again, now we know the antiderivative is x cubed over 3 minus 4x, and that's what we're doing as fundamental theorem part 2 is, when you do a definite integral, you're doing the antiderivative and plugging in your limits of integration. So we get 64/3 because you cube the 4 minus 16. The minus, plug in the 2, you get 8/3 minus 8. 64/3 minus 8/3 is 56/3. And -16 minus -8 becomes -8. That's -24/3. So you should get 32/3 if you do that correctly. Now, remember, you want to find the total area. So the net area would just be 32/3 minus 9, which actually would be 5/3. So my net area would be 5/3. And actually, that's what the calculator gets you. That's the result if you do the integral in the calculator. And remember, we're integrating the whole enchilada. That would be from -1 to 4 of x squared minus 4 dx. That would be the net area, and we get us 5/3. That's what the calculator would say. But for the total area, we do that in brown. The total area is going to be the absolute value of your negative area plus 32/3. And we care about that because we are going to talk about displacement and distance next week when you start doing some applications of the integral where you have a velocity function, and we want to be able to get both displacement and distance. So we have to be mindful of this whole total area kind of bit. So that's 9 plus 32/3, which will be 27/3 plus 32/3 or 59/3 if you do that fraction arithmetic correctly. So that's your total area. So again, if you look at the question down below, it's asking you, what is this? Well, we know that's 5/3. I just said that. But to summarize what we did for total area, we sketched the graph to ascertain that area that lies below the x-axis. If so, find the x-intercepts and partition your interval from A to B. Find those areas that are above and below separately by integrating f over those subintervals separately. So remember, we did the interval from -1 to 2, and then from 2 to 4. And of course, add the absolute values of those integrals. Anything that's negative, make it positive. Now you could do this in the calculator, the total area. You have to get a little bit clever here. And what you're going to wind up doing is we're going to wind up taking the absolute value. So to find it, and that's what we're going to talk about in class next time. If you actually integrate from -1 to 4 of the absolute value of x squared minus 4, and then in this case you actually have to use a calculator to get us through. But what happens when you do the absolute value of an expression, it is a transformation where it takes any portion of below the x-axis and flips it over the x-axis. And so then it gives you the proper total area if you wanted to do that. And then we'll have that discussion in class next time. But we should be able to get through pages 8, 9, and 10 pretty quickly tomorrow. And of course, wrap up the end of page 5. And then we could do some more practice with FTC. And then maybe talk a little about 7.1 on slope fields. Okay, I think that pretty much covers it.